Process capability is another aspect of statistical quality control. It is, however, although similar in appearance in some ways to our control charts, it is distinctly different, though. In the big picture here, what we're going to do is we're going to gather information about the performance of the process, but under a very specific situation, and that is when it is in control. That is statistical control. That's an important key thing. Now, just like all the rest of this, terminology is very field specific. So what I'm about to lead you through may change slightly depending on your particular field, but this is at least one view that is consistent in many ways with your Montgomery and Runger text. Okay, so part of our terminology that we need to be thinking about here is that as we take products and we design them, and in particular that we have to make something tangible here. We've done some marketing surveys, business studies to indicate a particular product and some general functional characteristics, but now when we get into design from an engineering perspective and a production perspective of the product or its subcomponents, we have to think about what those key characteristics are going to end up being. And from a manufacturing standpoint of those key characteristics, of course, what we're oftentimes very interested in are to specify our physical dimensions, our material characteristics or properties. That might be density, as well as those sorts of characteristics, as well as yield strength, tensile strength, compressive strength, maybe fatigue properties, that sort of thing. And when we specify these things, then we ultimately oftentimes end up producing a single value that corresponds to a desired level, right? So a desired value, as opposed to thinking about what limits there might be there, but a desired level. And in the terminology of many folks, this then becomes the nominal or sometimes target value. That is a very specific field-specific kind of set of terminology, because in my world, the nominal load in structural design is not what I would consider to be the target value. It means something a little bit different, and it may be just a shade of gray in some sense, but it is a little bit different. Same thing with sort of the notion of nominal resistance or nominal strength means something different. So you have to be very careful in how you interpret these words, and that's perhaps the most important thing to carry away, is that yes, have some sense of what these terms mean, but be aware that credible, competent people from different industries might be using a term that you're familiar with, but if it's not your normal context, at least think, oh hey, wait a minute, they might mean this in a slightly different kind of way than I'm used to. Okay, so the nominal or the target value is oftentimes what we're coming out from a design perspective. Now when we go to start thinking about producing something and establishing specification limits, or sometimes you might be calling this a tolerance limit, then we've got a question of that, how good or how close is good enough. If I want a part that's exactly 3 centimeters long, well, good luck with that. right? To get a process that's going to give you exactly 3 centimeters each and every time is not particularly realistic. There's going to be some natural variation as tools wear and other things happen in the process. So how close is good enough to maintain the functionality that we need to have? Right? And when we say how close is good enough, there's of course 2 different approaches that we could have, and that's a 2-sided approach versus a 1-sided approach, depending on, of course, the context that we're looking at. Right? And so in that kind of situation here, say a 1-sided, very often you might have a material strength specification limit that's 1-sided. For a concrete strength, for instance, we might be specifying 4,000 psi. For above ground structural members, for foundation work, that might be 3,000 psi. And we don't really care if we get concrete that's actually greater in strength. That usually just costs somebody more, and they want to provide something for free. Hey, go for it. But on the other hand, there are other kinds of cases where for instance, in certain structural steel applications, I not only care about what the minimum strength might be in terms of a specification limit, but because I'm reporting the yield or specifying the yield strength, I actually care about that being too high. And the reason why is that in seismic applications, I actually want the steel to go into the inelastic range and dissipate energy during the design level seismic event. And in fact, my design is counting on that to happen. And if instead someone were to substitute in a higher grade of steel, a higher strength level, what can happen is that the structure will respond in a different way than I had anticipated in my design scenarios. And so that different way can actually mean that the structure can experience more severe demands and create problems and behave in ways that aren't anticipated in the design. And so it's not always the case that material strength might be a 1-sided specification limit. There may be other situations in terms of that specific example. Another example of maybe a 1-sided specification limit might be, for instance, the level of contaminants in a water supply. So here a difference between the two is that the material strength might be a lower 1-sided specification limit, whereas contamination, of course, might be very much on an upper specification limit perspective, that I don't care if I have less, but I certainly don't want more than a particular value. But I don't need to have 2-sided, versus dimensional kinds of specification limits are very oftentimes going to be a 2-sided. Additional questions that come along with these specification limits are questions such as, you have a statement that says that, well, you're within the specs, but what does that mean? And does that mean that, for instance, all data is within the spec limits? Does it mean that a certain fraction is an allowable fraction, or a minimum fraction must be within the spec limits? What does it mean? And of course it's going to change entirely depending upon your particular situation, what that means. And so professions or areas of practice will tend to develop their own view of what that means in a specific kind of situation. And of course we sometimes articulate those in terms of standards such as ASTM standards, and of course lots of industries have their own particular standards that they establish for that meaning of falling within spec. Now if you fall within the spec, whatever that definition turns out to be, then you're in conformance, right? So what does it mean to be not in conformance is partly going to be a risk-related question, and that is, how serious is a failure to meet the specs? Is this critical? Do you have, say, catastrophic collapse of a building because something is not meeting the spec? Or instead, is this not really that such a big a deal to not meet that spec? So, you know, a way to re-ask the question is does the non-conformity cause the item to not be fit for purpose? Okay, and so if yes, then the nonconformity is a defect. And so if a certain part has to be a certain length within certain specification limits and it's outside of that, it screws up everything else about the assembly, then okay, that's a pretty serious issue. And so you say, well, it's now got a defect. On the other hand, if it's something like a shirt, then it may still be usable, right? So, but if the nonconformity leaves item still usable, then the item could be sold as a second. So it's still a shirt that has a blemish, is still functionable as a shirt. It may not be entirely fashionable to all people, and so therefore you'll still sell it. You can still make some money, maybe not as much because the market for that, the demand may be smaller. But now you just simply sell it as a second, and it's a non-conforming item, but it's not a defect, right? From this particular definition of defect, and that's a key thing. This is one specific definition of defect. It's not necessarily the popular definition, as in what people might be using out on the street who aren't involved in this quality control process capability investigation process. Okay, so a couple more aspects that we need to look at before we can get into back into some numbers here, and that is that we need to be thinking about a process approach as we start talking about process capability. That each, for instance, manufacturing step is a process, and from a flowchart kind of viewpoint, here's our step or our process, and there's going to be some sort of output to that, and of course there's going to be inputs into that particular process or step. And something called the systems diagram is going to chart all of these various inputs and outputs and the various steps. And so that system diagram is going to, system diagrams will chart the interconnections of various processes. And so our quality control efforts then are aimed at solving problems as well as maintaining consistent output. Right? And this becomes process control activities to not only solve problems which are alright, that's not exactly spelled correct, activities. That not only do we have to work at dealing with variability, but we also want to maintain consistent output as well. And so this notion of then statistical process control is to apply statistical methods for that process control, and that's the larger body of what we're working with. And again, here we got to deal with this notion that terminology is not universal across the board, not even between probability versus statistical analyses, but between, of course, industries and even groups within those industries. And so what you sometimes find is that variables data are sort of the analog of data of a continuous random variable, right, of that kind of nature. For example, data that comes out of measuring instruments. Good grief, my spelling is atrocious. Right, so contrast that to then attributes data, and that's data of a discrete nature and is oftentimes, for instance, counting numbers. How many have been produced? What fraction of what we produced are defective, the defective rate? How many total number of defects, or how many total number of blemishes do we have in that shirt? And is it feasible that to go to seconds we might say, well, we can have fewer than 3 blemishes, and we'll call that a second, 1, 2, or 3. But if we have more than that, then we'll automatically call that a defect and destroy the product. Right? So those are also important sets of terminology to be aware of and to be thinking about. Right, now, again, as we get into this notion of process control, then one of the ways we might approach process control is by looking at histograms of the collected data that we've sampled and measured. Okay, and so often what we're going to do with histograms are we're going to go directly to overlaying a normal curve, because so often the things that we collect are inherently normally distributed. Right? And sometimes it happens so often that we assume that the normal curve applies without stating it, and we draw our histogram based upon that without even caring about the appropriateness, or without investigating that, and without even actually drawing the histogram itself. We just assume that is going to be appropriate. So one thing that might look like is that, for instance, we have, on a two-sided view of the world, we've got an upper specification limit for a process, we have a lower specification limit for a process, and we come along and then draw our collected data as a bell curve, and of course we hope that the process average is centered halfway between the lower and upper specification limits. If we have a normal process, then we can start thinking about the odds that we're out of control, that we're out of spec, I should say, not out of control, but out of spec. And that's important kind of view, and so much so that let's look at a couple of different kinds of situations that we might have. And there's a certain amount of, okay, if this tail area is small enough, we might say, if it's 0.27% of the time that we're outside there, then that's probably within our plus or minus 3 sigma of our situation. That's kind of a good deal. So let's look at some other kinds of situations that oftentimes come up when we plot our various histograms here. And so it might turn out, now I'm just going to do an outline of the histogram, and note that in this case it's been shifted over. Clearly the center of mass of this histogram is over, so you got some sort of question of, since it's not, the process average is not in the center, then it's shifted towards one of the limits, in this case to the lower, then hey, there might be a particular issue in our process that we need to think about investigating further. And of course you could have one on the other side as well. Right? And other typical kinds of scenarios that you might end up with is that the bulk of your histogram is well within your specification limits, and the process average or centroid is reasonably close to your halfway between your two limits. But what happens if you have then your histogram showing some data points that are out beyond? Right? And that is of course not such a good thing. So outliers or out of spec. Do we have something going on? And sometimes you even see two of these little bumps, meaning that something else has come into play. For instance, maybe raw material has changed, or you've stopped the processing, you've done some maintenance work, replaced a part, and the recalibration afterwards didn't quite go the way that you were anticipating. So you always have to think about how the data was collected as you're doing this. And there's lots of other variations here. Sometimes the histogram has got such a small data set that's associated with it that instead of something reasonably smooth, that you instead end up with a chunkified histogram that indicates that you don't really have enough data set, or your bin width wasn't quite right, that you need to change your bin width, or maybe you need to collect more data to really have a feeling that, or a comfort level that you've got the process under hand.